Welcome back, my wonderful Allen High School students. We're going to be moving into our next chapter, and it's chemical reactions. Much like what we've seen in the past, good portions of this should be familiar from pre-AP chemistry. In fact, you can likely go on some websites and find those old pre-AP chemistry notes if you need them. What I'd like us to start with is a list of what I expect you to remember from pre-AP chemistry. And let's take a look at that. Your expected prior knowledge is to know how to balance a chemical reaction. That I think is pretty straightforward. That shouldn't be too daunting, and we will get lots of practice on that. So we want to make sure you can balance a chemical reaction. You should remember or recall or come ask me if that's not happening the terms endothermic and exothermic. Endothermic requires energy. Energy is a reactant. The surroundings get cold. Exothermic releases energy. Energy is a product. The surroundings get hot. I want you to revisit those evidence of a chemical reaction and bring back to your minds, and this you should know by now, that law of conservation of matter. The total mass at the beginning is equal to the total mass at the end. Now, what is a chemical reaction? A chemical change can be distinguished from a physical change by the type of bonding or attractions. So, if intramolecular forces, so within the molecule, that's the key there, molecular forces are involved, broken and or formed, it's typically going to be considered a chemical change. New substances, in this case, with different chemical properties. Remember, chemical properties are a potential for a chemical reaction to occur. For example, a chemical property of sodium metal is that it does react with water. So the property is the potential. The change is that it has happened. In a physical change, that's going to be typically a phase change. Dissolving can be a little tricky, but in general, when intermolecular forces are broken or formed, and we could put broken and or formed here, we would call that a physical change. The bonding structure within the molecules or the substance is the same. And I'll be honest, there are some that are a little bit difficult. For example, the dissolving of a salt. So remember, a salt is an ionic substance. The dissolving of a salt is typically considered a physical change. But ionic bonds are broken. So, you're actually breaking a true bond. And then attractions between water and the ion are formed, and heat is often released. And the release of heat is evidence of a chemical reaction. So, is it a physical change or is it a chemical change? Well, I would call that kind of ambiguous there. We're just not really sure. I wish I could remember the name of that character on Saturday Night Live. She was ambiguous. You couldn't really tell her gender, his or her, I guess I should say gender. And that's the case here. It can be really tough to figure out. So bear in mind that could be called a chemical reaction or a physical change. Now, let's move into how we represent such processes. And you have seen these before. We haven't actually made you draw them in pre-AP chemistry, but you have seen them in pre-AP chemistry. So let's take a look at the ways we can classify and represent reactions. There's two very broad categories. One category is a redox reaction, and the other is not a redox reaction. So a redox means reduction and oxidation. in this case, the oxidation numbers, we covered that earlier, they change. Electrons are lost. That's called oxidation. Oxidation is loss. And it has to be electrons are gained, and that's reduction. So in pre-AP chemistry, you remember the phrase oil rig. Oxidation is loss, reduction is gain. Now, if oxidation numbers change of an individual element, it's a redox reaction. If all of the oxidation numbers are the same, it's not a redox reaction. Now, within these two broad umbrellas of classification, we're going to look at different categories of reactions, ways to divide them up to make them easier to understand. So, how do we represent reactions? Well, we could have a molecular reaction. So, all that does is show molecular formulas. C2H4 gas, that's ethene. Is 2 carbons. Whoops, I want a plus there. Plus 3 oxygens yields 2 carbon dioxides. And both oxygen and carbon dioxide are gas, plus 2 waters, sometimes represented as a gas and sometimes a liquid. Now, this is always exothermic, and so I'm going to add heat as a product because heat is released because it's an exothermic process, right? So that would be a molecular reaction, just showing molecular structures, but that doesn't provide us quite as much information as we may need. So often you'll be asked to write the structural. Here's the advantage, the big advantage of the structural formula is that this shows us exactly what kinds of bonds are being broken. It takes to break a bond, and then it shows us exactly what types of bonds are being formed. Bonds are free, energy is freed when bonds form. And the molecular structure doesn't show us where we have single bonds or double bonds. So it doesn't give us quite as much information of the energy that is involved. Now, in this case, because it is exothermic, we free more than we break. So we're going to release more energy than what it takes to break. So that's another way we can do it. And then the third way, and this is always a little awkward for me to be honest with you, and I know it will be for some of you who are not the artists, or at least maybe you're the same level of artistic ability as I am, and that's to do a particle representation. So in a particle representation, we want to show the number of atoms, and you want to do it based on somehow on size. So I'm going to show my hydrogen smaller than my carbons there. So that shows my ethene. It's what we might call getting close to a space filling model. I'm not showing my double bonds there. I'm going to add to that oxygens, and we want a way to distinguish oxygen from our carbons. So if you don't happen to have colors, I'm going to do it without colors just to give you an idea of what it might be like on a test when you don't have colored pencils, right? So either make them hatch marks or color them in somehow. And I actually had 3 of those. So that's why they call these particle representations, because we're just using circular type particles to represent it. And then we make 2 CO2s. So I need the carbons with the 2 oxygens on either side. And then I would need 2 waters. So I'd need my little hydrogens with my big colored in oxygens. It's really not quite as complicated as they can seem. And it's quite important that you learn how to represent those well. All right? So that's how I would write that balanced equation. So I should have 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. So it's a nice, easy way to count that it's balanced. Right? Now there's one last thing I want to do in this introductory is I want to introduce you to net ionic reactions. This is yet another way we will represent these, and I will go into more detail in our next video, but I do want to introduce them. Net ionic reactions are a streamlined way of showing only the species involved in the chemical change. It's like what I call the good gossip. If you go to a party, you know what kind of tweets are happening at the party. It's like, ooh, wow, Anne's going out with Joe. Let's tweet that. That's only the good gossip. And that's what a net ionic is. Now, we can only show net ionic equations for aqueous, water-based reactions. And what we will be doing is dissociating or breaking apart into ions our soluble salts, our strong acids, and our strong bases. And you're going to have to rememorize those. And honestly, all you have to do is memorize a couple of solubility rules, and that's going to help us interpret experimental data and information that we will need at this level. And so we'll be doing more of those in our next videos. So until then, this is, as always, signing off.